Hi guys, so for this video we're going to practice electron configurations and box orbital diagrams for ions, right? Because this chapter addresses different types of ions. So you see that I've had a setup here for fluorine, fluoride where it gains 1 electron, zinc as is, and then zinc 2+ where we lose 2 electrons. So let's go ahead and write the condensed electron configuration for these. So F appears in the second energy level, right? So helium is the noble gas that we'll cite, and then it looks like it's 2s2, 2p5. So helium, 2s2, 2p5. That's where we're at with this. So if I were to represent this as a box orbital diagram, remember S only has 1 orbital. So this is my 2s, and p orbitals, there's 3 of them, right? So 2p. So it looks like I have 2 in the s2, so remember the rules, 1 up, 1 down. So for the p block, I have 5. So 1, 2, 3, and then they pair up, 4, 5. So I have 1 that only has 1 pointing up. All right, so F minus. That means that we've gained 1 electron. So where would that electron go? I wonder, right? It logically would go here. So we would now be writing an electron configuration, not just for fluorine, but for essentially neon, because we gained 1 electron. So helium, 2s2, 2p6 now. So if we were to represent this box orbital diagram, try to make them a little bigger. 1 up, 1 down for 2s2, 2p6. We'll have 1, 2, 3, 4, 5, 6 for the 2p on this one. Right? So this is how I would represent the box orbital diagram or the electron configuration for fluoride. Right? So I could ask you for either. For zinc, on the other hand, let's check him out. Zinc is right here in the D block, in the 3D block, and it looks like the noble gas that was finished before him is argon. So argon, put it in brackets, let's count. So we're at argon. Ooh, zoom out here a little bit. So we're at argon, and then the next row is where my thumb is, K, right? And that is 4s1, 4s2, and then 3d 10, right? 4s2, 3d 10, and we're at zinc. So 4s2, 3d 10. That's regular old zinc, right? Let's go ahead and represent that with a box orbital diagram. So how many orbitals are in the S? Just 1. How many orbitals are in a D? There are 5. Make it a little extra long. If you're like me, a lot of times you have to add an extra little block there at the end. So this is my 4s and my 3d. Why did I go down to 3d? Looks like it's in the 3rd row, doesn't it? Or it looks like it's in the 4th row, doesn't it? Remember, the D block starts at 3. The S block starts at 1s. The P block starts at 2p. The 3 block starts, or the D block starts at 3d. And the F block starts at 4f. So it looks like we have 2 S in the S, and we have 10 on the 3d. So 1, 2, 3, 4, 5. Remember Hund's rule, Hund's bus. They all space apart, and then they come together. So 7, 8, 9, 10. So that is there are actually 2 in each of these. Sorry, it looks a little messy. So that's how I would represent this box orbital diagram. For Zn2+, okay, your initial reaction may be to take 2 electrons from here. That's not true. What's actually happening is we have 1, 2, 3, 4. We are in the 4th energy level with the S, right? those 2 electrons essentially. This is just a generic representation. So the D electrons that are here are what? They're actually closer to the, right? This is the 3D10. These are actually closer to the nucleus. So what are my valence electrons? Out here. So you always take the valence first. So you take electrons from valence first when forming a cation. Oh, it's as sloppy as it is when I write on the board, isn't it? And I did note that I do have a squeaky chair, so I don't know how many things are distracting you from this, but luckily you get to replay this if you'd like. So I'm going to have to take electrons from my valence first. So it's sort of like, remember how I said it's like an everlasting gobstopper, right? I need to take something from this. I can't penetrate in there, get the electrons somehow, and leave this unscathed. No, you have to get the outside first. So you take electrons from the outside first. And how many electrons am I taking? I need to take 2. So in the end, what's only going to be left? Argon and the 3D10. So then we have our 4s, and it looks like that's actually going to be empty in this representation. And I have my 3D, that's going to be full still. Ooh, I'm not filling it up according to Hund's rule, am I? Spread out first, and then they pair up. Okay. So that's how we can represent electron configurations and box orbital diagrams for ions and cations and anions. So anions, you add one, cations, you're going to take a couple away, but when you take away from the anions, you make sure that you take away from the valence energy level, the outermost energy level. 4 is as far as we went out here, so we're going to take from 4 first. All right, I hope that helped everybody out. Good practice.